If we are looking at magnesium right here, the top number is the number that we need, right? So the top number right here is going to be our atomic number, and atomic number is always the same as protons. If the number would change, then it would no longer be magnesium. So if we don't have 12 protons, it's not magnesium. It can't be magnesium. Protons is the atomic number, is the identity. So protons equals atomic number, which also is the identity. If it changes, you don't have the same atom anymore. All right, excellent. So go ahead and give me a smiley face emoji or a yes in the chat if that makes sense from yesterday. Just a review from yesterday. Smileys, emojis in the chat. Excellent. Mary Jane, thank you, Ronnie. Perfect. Landon, Andrew, excellent. Awesome. All right, I'm going to go ahead and start sending out the notes. Here is the link if you are in my section, Mrs. Larkin. Here's the notes if you are Mr. Bangle's section. Again, make sure one link will work, one won't. So if one doesn't work, just try the other one. Or you can always get to it from the grades tab. Hi Hope, welcome to class. Go ahead and open up your notes. And then raise your hands. Remember, the reason we want to be doing our notes during class is because if you do your notes outside of class, then you only get notes credit. Whereas if you do your notes during class, you get both notes and attendance credit. So remember, we do need physical evidence that you are here. That is a part of Insight policy. You can't just log in and ghost us. You do need to actually be participating. You do actually need to be doing your notes. So go ahead and raise your hands. I will make sure 100% of you are responding in just a few slides. This is a reminder, please do not share contact info. Please participate often and well and behave appropriately. Don't forget that these sessions are being recorded and distributed for learning purposes that are listed here. We are on day 11 out of 60 officially, and our teens getting closer and closer to spring break. Oh my goodness, so exciting. We're taking a look here at the periodic table and electrons. Yesterday we focused a lot on protons, so today we're going to talk a little bit more about electrons. And you can see that we're about a third or a fourth of the way through our unit here.
So today we're going to learn more about the electrons and what specifically they do and how they act inside the atom. We're going to learn how to define what a valence electron is and what the octet rule is. We are going to go over the number of valence electrons in an atom and what that means. It will not be too difficult. It's going to be like a one definition kind of a concept to understand. And then finally, we're going to explain how the periodic table is organized by groups and what that means in relation to how many valence electrons each element has. All right, and as always, we're going to demonstrate this by completing our notes during class with an 80% or higher.
At this point, we do need you to go ahead and open up your notes then. So again, I'll send out those links again in case you haven't gotten them open yet. Go ahead and raise your hands once you do have that open. Let's go ahead and do a little bit of a brainstorm here. So we've been taking kind of a brief look at the periodic table throughout our last few lessons, which has all of the elements on it. But let's go ahead and begin to break down, what does everything on a square in the periodic table actually mean? So elements on the periodic table have a name, a symbol, an atomic number, and what is called the weighted average atomic mass. So we did learn yesterday how to calculate mass based on protons and neutrons, but we also mentioned that the number of protons and neutrons, the number of protons stays the same, but the number of neutrons can change, and that can change the mass of the atoms. Those are what are called isotopes. So you can have the same type of atom, an oxygen, with a bunch of different types of masses. There are oxygens with a mass of 15, oxygens with a mass of 16, 17, 18, 19, so on and so forth. But if you were to take all those different masses of all the oxygens in our world and average them out, that would result in an average atomic mass, which is not a perfect number. So you can see right there, that's not a perfect number because it's just an average. Go ahead, give me a smiley and emoji in the chat if that's beginning to make sense. Again, when we talk about the weighted average atomic mass, we're talking about just all the averages of all the possible isotopes. Excellent. All right. So tell me in the chat box, what is the symbol for oxygen? Let's make sure that we really know how to read this. What is the symbol for oxygen? Thank you, Thalia. Thank you, Shivani. Thank you, Dima. Excellent. Yes, it's actually a capital O. Make sure that you are capitalizing single letter abbreviations. Double letter abbreviations have one capital letter, one lowercase letter. So this one is going to be a capital O, excellent. And what is its atomic number? We learned just yesterday, and we reviewed this in our brain stretch. Which of these two numbers is the atomic number? Atomic number. Yeah, it's the number at the top right here. So this is going to be the number 8. This is our atomic number, and atomic number is also the number of what? The number of what subatomic particle? Protons, electrons, or neutrons? It is also the same as the number of what? Thank you, Julie. I see you in the chat. I see Landon. I see Thalia. Laura, Dima. Yeah, this is also going to be the number of protons. Hi, Karima. Welcome to class. Go ahead and open up your notes. You should be able to scroll up and find those. So the number of protons here. Again, this means that oxygen must always have 8 protons. If it didn't have 8 protons, it would not be oxygen. All right, so if it didn't have 8 protons, it would not be oxygen. It also would not have an atomic number of 8. So again, if atomic number changes, then so does the what. Starts with the letter I. What I just said, let's summarize that. If that atomic number were to change, so does the what. Thank you, Landon. I see you in the chat. So does the what of the atom. Yes, Dima. Isotrope does start with an I, but I actually was going for identity. Isotopes of an atom can actually all have the same identity. So you can have 5 different isotopes of oxygen based on its changing mass from its neutrons, but it can still be oxygen based on the number of protons. So yes, if the atomic number changes, then the number of protons changes, and therefore so does the identity. Let's go ahead and put that up on the board. And again, I know, you messed me up there, Ronnie. All right, so then again, that last number up here, what is the weighted average atomic mass? If I were to take all the isotopes of oxygen throughout our world and average them, I would get what number? Thank you, Landon. No, not 16. Take a look at the actual number here. Again, it's not going to be a perfect number. It's actually an average. The average means it's probably not going to be a perfect number. Thank you, Thalia. Thank you, Ronnie. Yes, Dima. Yes, Micah. Yeah, 15.999. And don't forget, units for atomic mass are AMUs, atomic mass units, because we like to name things in really obvious ways. All right, let's go ahead and talk a little bit more about what's going on in electrons for this lesson.
Start off simple. We're going to review some things about electrons we already know because that's what we're focusing on for this lesson. The electrons, their place inside or on the atom is the orbit outside of the nucleus. Remember, they're not part of the nucleus. They also have negligible mass, which means it's around 0 AMU. And their charge is -1, and they're only involved in bonding. So say we want to create a compound like water or something, or salt, then we need atoms to bond to each other, but the bonding is as if they're holding hands with each other with their electrons. All right, so the basic concept is that these electrons are moving very fast, and they're very tiny, and they don't weigh hardly anything at all, and their purpose is to attach atoms to each other. All right, but just some new stuff that we'll learn in more detail a little later on is that electrons, they're used to fill shells, and that's how bonding occurs. The smallest shell fits only 2 electrons. So as we can see up at the top right here, we have a helium atom that we learned about a little bit about yesterday, where it only has the one innermost shell closest to the nucleus that only needs to fill 2 electrons. Generally, every other shell that fits on top of the innermost shell will fit a maximum of 8 electrons, all right? And we will learn some rules that will guide us about how we figure that out a little later on. But let's learn a little bit more about something called the octet rule.
All right, so the octet rule tells you how many valence electrons atoms eventually want. So all atoms have a specific amount of valence electrons that they usually have, and we'll talk about how we figure that out in a little bit. But eventually, all atoms want to try to get to 8 valence electrons. Now, there's actually, that's not entirely true. There's actually some funky ones on the periodic table, but in general, the atoms we'll be taking a look at in our basic chemistry course are just ones that want 8 total valence electrons. And so this is why atoms actually actually bond, because not all atoms actually have 8 valence electrons. They might have 1, 2, 3, 4, 5, 6, or 7 valence electrons, and so they're trying to get to 8, and this is exactly why atoms bond. So what they're doing is, as mentioned, when atoms are bonding, they are actually sharing or exchanging electrons, and the whole idea of that sharing or exchange of electrons is because they're trying to actually reach 8 total valence electrons. Now this is what's called the octet rule. If you take a look at the prefix oct, like octagon or octopus, go ahead and tell me in the chat box, what number do you think oct means? Go ahead and tell me in the chat. OCT, that prefix there, like octagon, octopus, octet, should all mean what? Yeah, it all means 8. So anytime you hear the octet rule, you should think, oh, my atom is trying to reach 8 valence electrons. Now, let's go ahead and talk about that term a little bit more. The outermost shell is also called the valence shell. I already started using that vocab. But when we talk about the valence shell, we're ignoring everything on the inside. We're only taking a look at the outermost shell. We don't care about what's going on in the inside when we're talking about valence electrons or the valence shell. These valence electrons are the only ones involved in bonding. They're the furthest away from the inside of the atom, so they're the ones that are going to hold hands with other atoms. So not only does this determine how they bond, but it actually also gives them certain atomic properties. And we're going to see a little bit later how if you have the same number of valence or outermost electrons, you also have very similar properties. Let's go ahead and fill in the blank with the word octet. Only the word octet. Make sure you spell it correctly. Capitalization does not matter. 15 seconds.
All right, so we're going to practice, I'll just for one question, we're going to practice what valence electrons mean. So go ahead, your whiteboard tool should be on. Go ahead and use that box icon with the smallest font possible. Place a box around the appropriate definition you think that valence electrons mean. Are they in the nucleus, in the innermost shell, in the middle shell, the outermost shell, or in every shell? All right, think about where valence electrons are located. Thank you guys for everyone who's placing a box over that answer. And yes, that answer is the correct one. The valence electrons are in the outermost shell. So go ahead and for number 3, go ahead and click on the outermost shell for the answer for number 3 on your notes. All right, it is the outermost shell. And go ahead and raise your hand for number 3 once you're done. I'm going to set ourselves a timer.
Excellent. All right, let's go ahead and actually begin to practice this. So how many valence electrons does this atom have? You have your whiteboard tools. Again, we're only taking a look at the outermost shell. So go ahead and look at the outermost shell of nitrogen and go ahead and count up how many valence electrons do you see on the outermost shell and box it up on the board. All right, we're going to practice this a couple times. You're going to get lots of guidance for this first one, but by the end, you need to be able to do this on your own. So go ahead and circle the correct answer up on the board. I see Micah on the board. I see Julie up on the board. If you're on your phone, you can always answer in the chat so that you're practicing as well. Let's get answers up on the board. Thank you. I see Kathy up on the board. I see Monse working. Ronnie up on the board. Hope, thank you. Shivani, Andrew, Julie, perfect, perfect. I see Laura and Lacey in the chat. Yes, excellent, Dima. I see you up there. Yeah, perfect. So I'm going to go ahead and pause those tools before it gets too messy. So again, yes, if we ignore everything in, everything in the center here, all right, and only look at what's on the outside, we can see 1, 2, 3, 4, and 5 valence or outermost electrons. That is going to be the correct answer for number 4. Go ahead and answer number 4. You have 20 seconds to mark the number 5 for number 4. Just fill in the box with the number 5.
All right, so a bit more practice with valence electrons. All right, turning on the whiteboard tools back on again. How many valence electrons do we have for this atom? All right, I believe this atom is aluminum, but the identity doesn't matter. All we need to do, right, is count our valence electrons and indicate which number of valence electrons we have. Again, if you need to, you can respond in the chat. Yes, for this atom, we do have 3 valence electrons. Count them up. They're all on the outside there. 1, 2, and 3. So moving on, we're going to mark number 5. For number 5, the correct answer is 3. Go ahead and raise your hands to signify when we can move on. So this one's going to be a complete on your own. So please, guys, as a reminder, no answers in the main chat. If you have any questions on this, please let us know in the Q&A chat, and we will try to help you out. But I'm going to set us on about a minute for this one. All right, but when you are done with this one on your own, again, please raise your hands to signify when we can move on.
Let's go ahead and talk a little bit about number 7. So generally atoms will undergo bonding in order to reach how many valence electrons? So we said they have a set amount, but the reason they undergo bonding with those valence electrons is because they're actually trying to get to how many. Don't put answers in the main chat. If you want to check, we're in the Q&A area. Good way to remember this is think back to the octet rule. Think about what that prefix OCT means. Please answer number 7. You only need to put the number in the box. So just put your numerical answer in the box. You have 30 seconds to answer this. Go, go, go. 30 seconds to answer this. Okay, so now we're going to go ahead and talk a little bit about why these valence electrons or outermost electrons are so important. The reason is because atoms have very, very similar properties. Sorry. All right, atoms have very, very similar properties based on their number of valence electrons. So if they all have the same number of valence electrons, they tend to all act very similar to each other. So taking a look here, for example, these are what are called the alkali metals, and all of these metals, sorry, not all of these are alkali, but many of these are the alkali metals here, and these metals all have the same number of valence electrons. Valence, again, meaning the outermost electron. So taking a look here, they all have one valence electron. And when we have atoms that have one valence electron, these alkali metals, they tend to be very soft and can be cut by a knife. They tend to be highly reactive when placed in water. We're going to actually see that reaction in action in just a moment. And they also have low melting points. So let's go ahead and see how reactive they are actually in water. I'm going to go ahead and pop this video up on the whiteboard.
We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time...
All right, go ahead and tell me in the chat, what did you notice happening? What was that reaction like? Small splat. What about that last one, though? That last one was not small. Go ahead and tell me in the chat. Yeah, there was an explosion, right? Pretty much all of them reacted pretty intensely with water. Again, these first ones kind of just like fizzled in that water, but as we got more and more into the group, we saw eventually that we ended up with really explosive ones, right? You could actually see some light being pulled off as that hydrogen gas ignited that was produced. And then eventually we saw that it actually resulted in an explosion. Smiley faces, emojis in the chat box if that's beginning to make sense. Again, they might have had different degrees of how they reacted, but they were all eventually extremely reactive. All right, they were all extremely reactive to water, even though it might have looked a little bit different for each one. Excellent. So again, they have similar properties.
Electrons in a organized manner. All right, we are going to learn about how we constructed, right, in history of science, how we constructed the periodic table. So the elements are grouped based off their number of electrons, right? So we have group 1, group 2. We're going to skip the middle in this lesson, but basically then we have group 3 and 4. We'll go a little more detail about that in the later slide. But basically all we need to know right here is that the periodic table of elements is arranged by lining up these groups that they have in common in vertical columns, right? They don't go diagonally, that's something different, but in vertical columns, that's how we organize the groups of similar properties with the same number of valence electrons.
Let's go ahead and talk a little bit about how these groups are actually named. So taking a look here, they used to be called groups like 1, 2, 3, 4, 5, 6, 7, 8, and some parts were called the B groups and some parts were called the A groups. But that got a little bit too confusing as our periodic table got more and more complex and we learned about newer atoms. So nowadays we have a standard IUPAC is the name of it, a standard system where they're labeled from 1 to 18 left to right. All right, so you can see group 1, group 2. Again, these funny ones in the middle we're going to mostly ignore because those ones are kind of weird. All the way to group 13, 14, 15, 16, 17, and 18. Now, groups 1 and 2 are pretty easy to figure out. Group 1, they all have one valence electron, so hydrogen, lithium, sodium, potassium, rubidium, cesium, which we just saw in our video. These ones all have one valence electron. All the group 2s have 2 valence electrons. Again, the number of the group is related to the number of valence electrons. Now over here it does get a little bit more complex because now we're in the teens, group 13, 14, 15, 16, 17, and 18. But you can actually still see the number of valence electrons in the group number. It's just the last digit. So if you take a look here, what's the last digit in the number 13? Tell me in the chat box, what's the last digit in the number 13? Ignore that first digit. What's the last digit? Yeah, it's 3. So all group 13s, boron, aluminum, gallium, indium, thallium, they all have 3 valence electrons. Group 17 over here, they all have 7 valence electrons. So fluorine, chlorine, iodine, they all have 7 valence electrons, and so on and so forth. Go ahead and give me a green check, orange X if that's beginning to make sense. Again, for the teen ones, just look at the last digit. The last digit is still the number of electrons. Last digit is still the number of electrons. Green checks, green checks. You will need to be able to do a couple of these on your own. So please make sure that you are beginning to remember that. The last digit for the teen ones is still your number of valence or outermost electrons. Excellent, Thalia. I see you in the chat. Let's go ahead and take a look at an example.
I'm going to answer this question by first of all asking ourselves, what group or column is potassium K in? So potassium, or the letter K, is, I'm going to locate it for you, is right about here. What group do you see potassium under? What is that number at the top? Let's see some answers in the chat. Yes, it is in group 1. So because it is in group 1, right? It's in group 1. What does that mean about how many valence electrons it has? Exactly. I know I sound redundant because it also has 1 valence electron. All right. So that means for our number 8, our answer is going to be group 1 with 1 valence electron.
All right, let's go ahead and try this one out. So what group or column is sulfur in? Again, the group names, the group numbers are at the top in black here. What group is sulfur in? So take a look here. Sulfur is right here. And tell me, what group do you see that in? Excellent, Micah. Excellent, Shivani. Elijah, Kamara, Stephanie, yes, or sorry, Hope, yes, Dima, Landon, Ronnie. Yeah, it is in group 16. Perfect. All right, so taking a look here, if it's in group 16, again, we said the teens, you only need to look at the last digit. So what is the last digit in group 16? That'll be the number of valence or outer electrons. The last digit, last digit. Again, you're going to need to be able to do this on the next slide by yourself, so practice with us. Yeah, the last digit here is just the number 6. So here we go, taking a look here, sulfur only has 6 valence electrons. It's not 16, it's only that last digit, which is 6 valence electrons. Again, because of this new way, relatively new, right? It's been around for a while, but this newer way of how we name the groups. So this is going to be the answer to number 9. Go ahead and take 20 seconds to answer that and raise your hands. Last one is then what group is boron in? Don't put answers in the main chat if you want to check. We're in the Q&A chat, so find what group is boron in, and then again, how many valence electrons does that mean? Again, for the teen ones, look at the last digit of the group. This will be number 10. Make sure you have both of the correct answers, otherwise the computer will mark it wrong. I'll go ahead and give you 40 seconds to answer this one, a little bit more time. Raise your hands for number 10.
How to count them, what the octet rule is. We're not really using octet rule, but we do know it means a rule of 8. We did go over the periodic table in relation to those valence electrons to learn how they're organized with their associated properties in the periodic table together. All right, go ahead and when you're done with the notes, go ahead and tell us what score you got in the chat. so we can shout you out. And yeah, be sure to submit your notes as well.